Good morning, everyone. It's really nice to be here. This is one of my favorite conferences, and I'm really happy it's back after what's been a few rough years. I'm going to talk about QEC on QCCD, and my kind of metaphor I'm working with is cooking up corrections. So a little bit of background on what Quantinuum is. We're a fairly new company because we're the result of a merger between Cambridge Quantum, which is responsible for quantum software such as PyTicket, and Honeywell Quantum Solutions, which has been making ion traps for a few years now. We have offices all over the world, and here at this conference we have representatives from both our UK office and our offices in Colorado. I myself live in Colorado. So we've only been around for a few years, but we've kind of done a lot in terms of demonstrating fault-tolerant protocols. And one of the reasons for this is we have a really, really flexible architecture. So I'm going to give you an overview of this architecture and highlight some of these demonstrations we have done. And if you take nothing from my talk, I hope that you get that we have a very flexible architecture for realizing fault-tolerant protocols. Now, there's a lot here, but thankfully it takes a village. And I have several colleagues in the audience, but most notably, Kieran Ryan Anderson will be talking after me, and he will talk about our work related to logical two-qubit gates. And Ben Krieger is also here, and he recently put out a paper on a fault-tolerant logical algorithm doing one-bit addition. I believe he has a poster. So if you have questions, of course, come to me, but these guys are also here, and they know a lot about all the work I'm going to discuss. Okay, so this is a hardware talk a little bit. So before I get into the so-called QEC recipes, let's talk about the kitchen and the ingredients we're going to use to do quantum error correction with. So QCCD stands for Quantum Charge Coupling Device, and So we have 3 commercial systems that are built on 2 different styles of traps. These are surface electrode traps. And we use ytterbium-171 qubits that have a hyperfine splitting, so they're pretty resilient to magnetic fields noise. Each qubit has a accompanying ion of a barium-138 cooling qubit, which helps reduce noise from heating and stuff. So kind of the features of our traps are we have these different zones. So highlighted here in blue, these are our gate zones. That's where all the action happens. It's where you have mid-circuit measurement, you have 2-qubit gates, you have single-qubit gates. And then we have these green zones over here that are storage zones where you can actually move our ions out of the way, and in this way do things like mid-circuit measurement without disturbing the quantum information on the qubits we're trying to measure. We kind of have this joke at Quantinuum that we're really, really good at naming stuff. So rather than naming our traps after birds or trees, we just say H1 and H2. So we have H1-1 and H1-2. Those are our 2 traps built on the H1 surface trap as seen here. Each one of those has 20 qubits. And just earlier this year, we released our H2 system, also affectionately called Daytona. Let me do this. There, that'll be easier. And it is a 2-dimensional trap where we've basically taken these 2 surface traps and stacked them on top of each other, and it has this loop here. And it has 32 qubits. So what are some of the differentiating features that this architecture gives you? Well, we have all-to-all connectivity. So because we are able to shuttle our ions around, every qubit can talk to every other qubit, and this allows you to implement pretty high number of qubit algorithms on a smaller device because everything can talk to each other. We have high fidelity gates, and in particular, we have very low measurement crosstalk, so pretty good noise on our system. We have the ability to do arbitrary angle single and 2-qubit gates. And then what's most relevant to the work I'm going to discuss today is our ability to do mid-circuit measurement and reset, and then conditional logic. So again, we can, in the middle of a circuit, measure a qubit, take that classical bit of information, and dynamically change circuits in real time on the fly. So here's a cartoon On the, left, we have just a circuit diagram, and I've labeled the qubits red, green, and blue. And on the right, we then have kind of a picture of the trap, and we'll kind of look at how, as we execute this circuit, what's going on in the trap. So first, we're going to initialize our qubits. All of our gates are driven by laser beams. The next step, we're going to perform a single qubit Hadamard on the red and the green qubit. So you'll notice that they are in the gate zones ready to go. So we can go ahead and perform that gate. In time step 2, we want to perform a CNOT between the red and the green qubit, but you'll notice that they're located spatially far away. So what we are able to do is we're able to move that green qubit over into a gate zone with the red ion and join those ion crystals together. Now they're together in a gate zone, and we're able to perform a 2-qubit gate on them. The next step, we're wanting to perform a 2-qubit gate on the red and the blue ion, but they are spatially far apart, and there is a green ion in between. And what our system is able to do is physically swap the qubits in the well, move the other qubit over, and reposition it. And now we're in a position where we can do the 2-qubit gate on those faraway ions. And this is exactly what gives us our all-to-all connectivity. Finally, in time step 4, we want to measure the green qubit, but we of course don't want to disturb the information that is on the red and blue qubits. They're separated in different gate zones, so we're already ready to go, and we're able to measure only the green ion without disturbing the red and the blue. So these are some kind of system specifications for our 3 commercial systems. Again, we have a great naming of H1-1, H1-2. The first H1 or H2 differentiates what trap the computer is built off of. And then our H2 system has a few more qubits. So all of this information is published on our website online. There are 3 different machines, so there's 3 different noise profiles there. But yeah, I think we have pretty good error rates. I guess I'm supposed to note that in 2024, we're expected to have over 52 qubits on our H2 device. This is an industry talk, so I have to show you a roadmap. Everyone in industry has a roadmap. I've already talked a little bit about H1 and H2. From there, our H3 device is hopefully going to move to this grid-like structure. So we'll have this 2D geometry where we're hopefully going to shuffle ions around. We have recently this year been able to demonstrate this. So this is an actual picture from the lab of one of our test beds where we're able to show dual species junction transport. So dual species means I have an ion that's a qubit and an ion that's a cooling ion, and I'm moving them around this grid as you see here. Only one of the ions is illuminated, something lasers. So yeah, we are well on our way to demonstrating how we can scale up this architecture. And we affectionately call this Pac-Man. This is H1-1 and H2-1 illuminated with that Pac-Man prototype. And I just really want to show this slide because I think it's cool. This is not what I do in my everyday job. And I think it's just amazing how the experimentalists are able to see this. So in the first slide, you see all of the ions in that linear trap lit up. In the second one, you see all of the qubits running around that racetrack in Daytona. And then, yeah, the junction transport is also, it's just cool. Okay, so now that we hopefully have a little bit of background about what our system can do and that we move things around and we can do stuff very dynamically, let's go into our first recipe, which is this repeated QEC cycles using the Steen code. So the work I'm going to talk about is from this paper, Realization of Real-Time Fault-Tolerant Quantum Error Correction. And the key ingredients we use are mid-circuit measurement and reset, conditional logic, and then something called extended chasm features, which I'll talk about in a second. So this paper is a little bit old. It came out in December of 2021. But if you are not familiar with it, I highly recommend you read it, especially if you're a student. me and my colleagues Kieran and David Hayes, we took a lot of time to write this and put all the dirty details into it. There is lots of pictures, there's lots of examples, there's pseudocode. If you want to know how to implement a QEC code on actual hardware, I'm very proud of some of the detailed descriptions we put in here. There's a lot in this paper. Most notably, we did repeated rounds of full QEC cycles. And when I say a full QEC cycle, I mean I'm measuring enough syndromes to be fault tolerant to both physical and measurement errors. We did real-time decoding in the form of a logical lookup table. And we also did a non-fault tolerant encoding of a magic state. So for this talk, I'm going to focus on this main experiment here, which is the QEC cycle experiment. I'll walk through this diagram, and then we'll look at some results. So at the time of this work, we had 10 qubits in our trap. And so with 10 qubits, you can implement the Steen code, which is a 713 code. I need 7 physical qubits to get 1 logical qubit, and I'm a distance 3 code. So I should be able to detect and correct every single error that can occur. So here I have a picture of the code. If you're not familiar with the Steen code or the color code, under each one of these plaquettes, there is both an X and a Z type stabilizer that I have to measure. And I have 3 qubits. Again, I had 10 in the trap. I used 7 to make the logical qubit, so I have 3 qubits left to make these syndrome measurements. So the first thing I want to do is I need to encode this information in some way. And we use this circuit thanks to Goto. And the first half in red is this encoding circuit, but it's not fault tolerant. So, you know, in the literature, there's a few different ways you can encode logical qubits. You can measure the stabilizers, but one advantage of an encoding circuit is you might be able to reduce circuit depth a little bit, and so that's what we were trying to do here. This half is not strictly fault tolerant. There is a non-zero probability that you could have a weight 2 error coming out of this circuit, but kind of the ingeniousness of this Goto scheme is if you add this logical check at the end, you can catch any of those higher weight errors you can catch them as they come out, and that gives you the ability to either post-select or start over. In our case, we didn't do any post-selection. We just measure this out, and if it was a 1, we just start over, and if it was a 0, we can move on. So we did this as a repeat until success type style circuit for up to 3 times, because that was kind of the win between how long this circuit would take to execute and what fidelity we got out by adding this. So this circuit itself encodes the logical 0 state. In the experiment, we're going to look at all the logical polybasis states. So one feature of the Steen code is that all my Clifford gates are transversal. So I'm going to apply a logical rotation to get whatever state I'm looking at for the particular experiment. So for example, if I wanted to look at the logical plus state, this operation here would be a transversal Hadamard. And yeah, once I've prepared my logical state, I'm ready to go do some QEC cycles. So this is a little bit of a beast, and it is, given that it's a flow chart, that means it's dynamic, right? There are different branches of the flow chart that I can go down. If you're familiar with the surface code, then you probably know that I can order my syndrome measurements in such a way that I'm fault tolerant. Errors that will occur will propagate in such a way that I can catch them. That is not true for the color code. The color code suffers from these errors, known as hook errors, that can occur in the middle of your syndrome extraction circuit and propagate to higher weight errors, rendering your code non-fault tolerant. Now, the workaround for that is usually this concept of a flag qubit, that you can flag your syndrome and in such a way identify or catch these hook errors when they happen. But this requires extra qubits and extra circuitry. So this scheme here is actually due to Reinkart, and what he was able to figure out is that he can actually use the ancillas that are measuring the syndromes themselves to flag each other. Kieran likes to call these flagsillas. So I have these 3 ancilla qubits that are measuring 3 syndromes up here, but you'll notice that they're entangled to one another, and in this way, they're serving to flag each other. So this is maybe a little bit simpler of a diagram to look at. In the first half of this circuit, I am measuring this X stabilizer and these 2 Z stabilizers. If my syndromes are trivial, then I'm going to move down here and measure the remaining 3 checks. If they aren't trivial, then I'm going to move over here and measure all of the checks using these unflagged circuits. And these unflagged circuits, you might look familiar. They're kind of the normal way of measuring a weight 4 stabilizer. Similarly, if I detect nothing, then that means I have not seen any errors, and so there is nothing to decode on, and so I can exit this QEC cycle and choose to repeat it or choose to not to. Or if I detect something here, I can again move to these unflagged checks. Once I have my syndrome information, I'm going to send it to our logical lookup table. Okay, so why do we need all of this rigmarole exactly? I kind of already alluded to this idea of these hook errors. And I apologize because it's a little bit of a backwards argument, but I think everyone here is going to understand it just fine. Here I have these 2 unflagged circuits, and I have 2 different error configurations. Up here I have errors, X errors on qubits 2 and 3, and down here I have an X error on qubit 7. But when we look at the syndrome information that comes out, we see that they're the same. At the top I have 0, 0, plus 1, 0, 0, 0, and the bottom I have 0, 0, plus 1, 0, 0, 0. So same syndrome information from 2 different error configurations. Now, if you've been paying attention, you'll know that this is a distance 3 code, and I'm showing you a weight 2 error. So you might be saying, Natalie, it's a weight 2 error, it's a distance 3 code. Like, why am I even worried about this? But if we look at the origin of how I actually got that syndrome information to begin with, we can see that it actually comes from 2 different physical events happening at different parts of the circuit. So the top one here is, again, this so-called hook error that happens in the middle of the circuit and propagates in a bad way to a weight 2 error. And the bottom one here is just a very simple error on qubit 7, gives me some syndrome. But when we look at the collective syndrome information between the flag checks and the unflagged checks, we see that there is a difference. Up here we get 0, 0, plus 1 versus 0, 0, plus 1. And it's these 2 sets of checks that we're able to feed in our decoder and differentiate between these 2 events, which makes the entire procedure fault tolerant. Now that's a lot. There's a lot of conditional logic here. There's a lot of processing of information, and you want to run this on a real quantum computer. At the time of this work, what we had available to us is OpenQASM 2.0, which is a great language, but it is not as expressive as we need to demonstrate something like this. So we took this to our software team, and they were able to come up with these OpenQASM 2.0 extensions. And what they are is they just add to the OpenQASM language and make it a little bit more expressible. So I can do things like if statements conditioned on a single classical register. I can say if not. I can compare, is this classical register higher or lower than some integer? Then I have also these binary operations, in particular this bitwise XOR, and that's how I'm able to actually detect changes in syndromes on the quantum computer. Now, I promise I will show you the decoder in a little bit, but for now, we'll just get back to this flowchart. So once we feed our syndromes into our decoder, we can update a poly frame, which we'll keep track of in software, and we can, again, choose to repeat these QEC cycles as many times as we want, or we can conclude the experiment and go to a logical measurement. So we're, again, going to rotate to whatever basis we're trying to measure. We can then measure our data qubits, construct a final syndrome from that measured data, send it back into the decoder, get a final correction, and calculate our final output. So here are the experimental results. We looked at all 6 poly bases. So here's the X, Y, and Z bases. And over here on the left, we have the logical error rate and versus QEC cycles. 0 QEC cycles in this setting means that I just did that encoding circuit. I encoded, I rotated to whatever basis state I'm looking at, and then I measured out. For all of the basis states, we went out to 4 QEC cycles, but for the one that we found the noisiest, we actually went out to 6. With this, we were able to fit it to some exponential curve, which makes sense because the deeper the circuit, and these circuits get quite deep as you increase the number of QEC cycles, you'd expect the illogical error rate to decay exponentially. And from there, we're actually able to pull out the fidelity of both the spam and the individual QEC cycles. What's notable here is that our physical spam at this time was just slightly worse than the logical spam we got. In the next talk, you're going to hear about how things have improved since then. So because we don't see a huge difference between the plus and minus states here, we're actually able to assume kind of an asymmetric depolarizing logical error channel and construct that channel by combining these different states. And we see about a 3% error rate, total error rate per QEC cycle. We also compare this to a very detailed error model of our device. So this is powered by this Pecos package, and it is really detailed. It does not just do gate depolarizing noise. It's able to do complex things like idle and transport noise. We send everything through the compiler and get the different steps that the qubits actually go through when the circuit is executed. And from there, we're able to model all of the transport noise, things like leakage. We can do coherent and incoherent dephasing rates. It's very, very detailed. And we see that the simulation results match pretty well with the experimental results. So with the simulation matching the experiment, we can kind of have a bit of faith that the simulation is capturing at least pretty well what's going on in the machine. And that means we're able to calculate things like a logical error budget. So by varying the different noise parameters and looking at how they contributed to the overall logical error rate, we're able to come up with this error budget. And it's maybe not surprising that a big chunk of our error budget is related to this dephasing error. And that is because, again, we move our qubits around, and when you move them around, they incur this kind of Z-type noise. We also don't operate exactly at 0 magnetic field, so there are magnetic field insensitivities that our qubits will suffer from. From there, we see another big chunk is just straight up unitary gates. We're always trying to improve our 2-qubit error rates. We also then in simulations are able to kind of look at where is that point where we'd be passing pseudo threshold or hitting some sort of break-even milestone. So here, this x-axis is just some physical scaling rate, which means I'm going to scale all the current error rates by whatever that number is. So you see here it's 1, and this red is our current error parameters. So this point up here represents all the data that I showed you on the previous slides. And so we see if nothing changes and we keep kind of our current errors as they are and we just start to scale them down, it's going to take a while before we pass some sort of pseudo threshold. But if we're able to focus on particular errors, most notably leakage and this dephasing error, if we're able to scale everything by the same amount but leakage and dephasing by 1/10 more, we see that we're able to pass that break-even point much sooner. Okay. I promised I would show you the decoder. This is our actual chasm, pure chasm with extension, lookup style decoder. This is, I'm going to emphasize, a logical distance 3 lookup decoder. And the point of this slide is to not go through the logic and not to have anyone actually understand this, but for you guys to go like, oh my gosh, what a pain in the butt. This is certainly not scalable. This must have been a pain to code up. There's got to be a better way. And so with that, we'll go to recipe 2, which is real-time algorithmic decoding. And the key ingredients here are minimum weight perfect matching and WASM, or WebAssembly, and our hybrid compute environment. And the results for the repetition code that I will show you here in a second are in our H2 benchmarking paper that came out earlier this year. So a big part of quantum error correction is this classical decoding problem. The name of the game is you're going to measure some syndromes, you're going to feed that into some sort of classical algorithm, and you're going to hope that classical algorithm solves things quickly enough that you're able to continue your quantum computation. So this puts several demands on classical coprocessors. There's a lot of great work out there on how to make decoders fast and how to program them on FPGAs. One of the advantages of ions is we are a little bit slower, so we have a bit more time to figure things out. And so some of the demands this puts on a CPU, if you want kind of a playground to investigate decoding problems, you need to be doing things fast. You need to be expressive. A lot of these decoders require things like Dijkstra and Blossom, these very computationally heavy classical subroutines. If you want to do it on a commercial system, then you need to be able to deliver custom code without involving full stack modification. If I bugged an experimentalist to do something for me every time I wanted to test out the code, I would make them angrier than I already do. It should be secure. You don't want people hacking your quantum computer. And then finally, you need to meet all these requirements without impacting the performance of the quantum processor. So with these requirements in mind, our software team came up with this hybrid compute using WebAssembly, or WASM. And what this really allows is all the rich complexity you have in classical programming, you now have access to on your quantum machine. So things like public functions, complex data structures like arrays, calling libraries and subroutines like Blossom. You now are able to write more or less as complicated of a program as you want in some higher language like Rust or C++, compile it to WebAssembly, and then within your QASM actually make these classical calls. So this is a little cartoon of how the development of this works. The quantum developer will in tandem write their classical algorithm, such as their decoder, as well as their quantum algorithm, like their QEC code. They'll submit both through the API, and then the classical part will run on the QPU, the quantum part on the, classical part on the CPU, quantum part on the QPU, and you'll get your output. So here is an example of a very, very simple, these are the same thing, just two different ways of doing it. This is Rust that will compile to WASM, and this is a distance 3 lookup table repetition code. So here you see I'm using a match statement. I'm going to put an integer in, which is a syndrome, get an integer out. Over here, I'm just showing how you can use more complicated data structures. Here I'm using a Rust hash map, which is kind of like a Python dictionary if you're not familiar with Rust. And again, I integer in, I can put a polyframe in, and I can do some of the more complicated classical computing on the side. Here's what the stitching of the WASM and the QASM looks like. Over here, I have a pure QASM implementation. So this is, again, repetition code where I'm measuring some syndromes. And then I just have a simple if statement, 3-line if statement lookup table. But over here, same code, but I've replaced these 3 lines by that WASM call that says decode. And just to go back, this function's named decode. My WASM call in here is named decode. Now you might look at this and say, well, is this really that impressive? You took 3 lines of QASM that were pretty easy and replaced it with 1 line of WASM. But you can imagine if this was a larger distance code, or if I was doing a more complicated style decoder, that this would be a really, really powerful tool. And in fact, this was this tool was maybe not necessary for this demonstration, but definitely enabled this demonstration of a repetition code on our H2 device. So as I said, we released our 32-qubit machine earlier this year, and as we're preparing for the release, we're doing all the normal tomography things and benchmarking things, and we're thinking about what type of interesting algorithms would people like to see. And what we thought would be interesting to showcase the features of the device are to take a 32-qubit machine and implement a distance 31 repetition code. The repetition code has a lot of features that full QEC codes do, even though it's not a full QEC code. But you measure stabilizers, you can decode using minimum weight perfect matching, you calculate logical fidelities the same way, and hopefully you can increase code distance and see an improvement in logical fidelity. So we took 31 of our 32 qubits and defined them as our data qubits, and then we took that remaining qubit and made it our ancilla that measured all of the syndromes in serial. We recorded those syndromes, and yeah, every time a syndrome was measured, we sent it over to our WASM side, and then at the end of the experiment, we are able to do a full minimum weight perfect matching on that syndrome volume. So on this graph here, we have these, the code distance. For each one of these, we went out to 9 rounds of syndrome extraction. That's kind of an arbitrary number. And then you see the logical fidelities here. How we were able to construct all the lower distance codes is because we recorded all of the syndromes. And so what was actually ran live was this distance 31 code. And from all that information, you can look at all of the smaller codes by keeping track of the syndromes and the qubits they're associated with. And that is how you're able to build all of the lower distance codes. Okay, repetition code is great. It's a wonderful tool, but it is not a full QEC code. So in addition, we are looking at surface codes. And in addition to just being able to do algorithmic decoding, we're really interested in how much parallelization in syndrome extraction is necessary. So here are some preliminary results where we looked at 3 different flavors of the surface code. We looked at surface 17, which means I have 8 ancilla for a dedicated ancilla for each syndrome I need to measure. We looked at surface 10, which means I have 1 ancilla to measure everything in serial, much like the repetition code I just showed you. And then we looked at surface 14. And surface 14, at first glance, might seem like an arbitrary thing to look at. Why would you just pick 5 ancilla? That seems a little weird. But if you recall the trap diagrams I showed you at the beginning, we have 5 gate zones in this particular machine. So 5 syndrome measurements is the most we can actually make in parallel at any one time. So we're looking at the most ancilla you can have, the least ancilla you can have, and the most syndromes you can measure at any one time. Again, this is pretty early data, but I don't know that I see a huge difference between these different implementations. In fact, I'm definitely picking and choosing data right now, which is not fair, but this point right here is surface 10. Surface 10 is performing the best at this particular location. So how much parallelization do we really need? Now, I could make some arguments about threshold calculations and why this assumption is important and things like that, but I'm going to take a much more practical stance and say when we're talking about scaling up devices, it's really expensive to have these gate zones. It's really hard to produce. It's a hard challenge for our fabrication team to know where and when to put them. So answering questions like this so that we have a better grasp on how much parallelized syndrome extraction is necessary is really important as we look to scale up. Finally, I'm going to go to our third recipe, and our third recipe is not so much a recipe as much as it is me trying to very quickly highlight some outstanding work that I won't have time to talk about. This is our work towards logical algorithms, and I'm going to highlight these 4 papers that all came out fairly recently. So the first one is this. Let's see if I can get the title right, because it's a mouthful. Advances in Quantum Compilation, a demonstration of magic state distillation and repeat until success protocols. At the heart of this paper is the ability to leverage the LLVM compiler toolchain, which is really good at optimizing control flow logic, to realize these more complex fault-tolerant schemes that require control flow logic. So we did 2 experiments in this. The first one is magic state distillation, where we realized this 513 Bravian-Kataev scheme. We did this on 5 physical qubits, so this is at the physical level, not the logical level. But we were able to write this in Q# and compile it to QIR, or quantum intermediate representation, and demonstrate the ability of this compiler toolchain to execute this stuff well. We did not see distillation. We did not see that the output fidelity was higher than the input fidelity. However, this is to be expected. This is on the physical level, and this circuit is fairly deep. So you wouldn't expect a circuit that's made out of 20-something CNOTs to outperform just a simple state prep that's made out of 2 single qubit gates. But nonetheless, it kind of fit with the theoretical curve of how much we should expect successful distillation. Well, I should say measuring non-trivial syndromes is what I mean when I say distillation attempts. Measuring trivial syndromes, I mean. And again, it shows our ability to execute these kind of complex control flow structures. The other half of this were these repeat until success protocols. So about 10 years ago, Patznick and Swory introduced this concept of repeat until success to implement different unitaries. Magic is very expensive, so once you have a magic resource, you better spend it wisely. And these repeat until success protocols try to achieve that. So they implement different unitaries by using ancillas. And we looked at this particular circuit written 4 different ways. So we have a high-end user language, either OpenChasm with extensions or Q#, and the Q# we chose to write the logical loop 2 different ways, either with recursion or 4. We have 2 different compilation targets, OpenChasm or QIR, and then 1 hardware. And what you see here is that not all things are equal. Even though this is all the same circuit and hopefully the same logic, you have different machine performances based on the implementation. Next work I want to highlight is from our group out of the UK. Chris Self and David Amaro looked at this family of codes known as the iceberg code. It's a error detecting code. And what they were able to do is pass actually logical quantum volume of 2 to the 8. They did this on our H1-1 device. So great example of logical benchmarking. Later in the year, our quantum chemistry team led by Kentaro Yamamoto took that same code and encoded a quantum phase estimation algorithm. So he compared an unencoded version, which uses 3 physical qubits, to the logical encoded version using 8 physical qubits to give you 3 logical qubits. And what he was able to see is that the encoded version got closer to predicting the correct energy. So here's the energy that you'd expect for the particular problem, and we see that the encoded version did better than the unencoded version. Finally, this paper came out just a few weeks ago. The iceberg code work I just talked about does not do everything strictly fault tolerant. And this work does a full algorithm doing 1-bit addition, and it looks at both a non-fault tolerant implementation and a fault tolerant implementation. And in particular, you see that the non-fault tolerant implementation has a higher error rate than the fault tolerant implementation. So that's really cool. It's an example of a fully fault tolerant algorithm and also demonstrating that fault tolerant principles really can help you. So this is kind of a not necessarily generic wrap-up slide, but where are we on the path to demonstrating error correction? This is kind of ingredients that you need. You need long coherence time, which means you need the ability to do repeated rounds of error correction. You need low error rates. You want to be not at pseudo threshold, but below it. You need a fast and scalable decoder. We're not there yet, but we certainly have the infrastructure to start looking at these things. You need a universal gate set, so you need to be able to encode magic states and hopefully distill them at someday. You need speed. Can't take forever to do things. And finally, you need to put it all together. And we're starting to see some features, as I showed you in the previous logical algorithm slide. It takes a village. I really want to highlight in particular, I work very closely with the software team. They give me a lot of the tools that I get to use to implement some of these things. And I couldn't do anything without our wonderful hardware teams that actually build these awesome machines. Finally, again, industry talk. We're hiring. We have some QEC positions open. We also have internships open, both in QEC and other kind of control flow stuff. So please come talk to me or any one of my colleagues if you're interested in that. Finally, you don't have to work at the company to run on H1 or H2. There are two different programs, one through Oak Ridge National Laboratory and the other one through Microsoft Azure, where you can run directly on our device. Everything I showed you was done on a commercial system. We do not, all the stuff we do interleaved with customer jobs. So everything I showed you, there's no like secret feature that I have access to that users don't. You can go directly run some of this stuff yourself. And with that, I think that's all I have.
Thank you, Natalie, for excellent talk. So we have time for a few questions. There's one question on the back.
Hey, yes. Can I just yell? So thank you for the very
We can barely hear you.
Okay.
Maybe, yeah, Mike's coming.
No, that's fine.
Yeah.
Thank you for the very nice talk. You commented on the fact that it's kind of hard to increase the number of gate zones. I'm just kind of interested in trying to understand that a little bit better. I mean, can you just like fab a bigger chip, or is it kind of all the control infrastructure that goes into controlling each gate zone? What are kind of the challenges involved?
Yeah, so I am not an experimentalist and I don't work on the fab team, but I think I have an okay answer. There is a lot of optics that go into this, right? There is a lot of different beam lines. There's a lot of shuffling and stuff you have to do. So it's a lot of stuff to get right. One of the cool features about some of the traps, I think Kieran's probably going to talk about this a little bit, is once the trap is made, you can't change the gate zones, but you can add in more qubits. And so I think that when they design these things, they really look at the ratio of how complex the optics are, how many qubits you can get on there, what are the fidelities, because my understanding is we can add more stuff, but that makes things harder to control, which then makes the error rates worse. And one big thing that Quantinuum believes in is not increasing qubit number, but also decreasing fidelity. If we're going to increase the qubit number, we're going to maintain or improve the fidelity. So I know that's like not the best answer, but it's kind of a really complicated optimization problem where you're looking at how many qubits you can have, how many beam lines you can have, and also are you maintaining that high fidelity error rate.
Maybe we can take one online question while the mic is moving around. So is the trade-off between serial and parallel syndrome extractions for surface code a sign that there is high crosstalk between gate zones?
So I guess I'll make the comment that I don't know, even though maybe I alluded to, that is preliminary work. There's a lot more analysis to be done on that. I wouldn't attribute it to high crosstalk. We actually have very low crosstalk between gate zones. That's a feature of, because we move qubits far away from each other, different ion trap architectures don't have that same ability. As for why they're close, for the difference between, say, surface 14 and surface 17, I think that the transport dance, as we like to call it, meaning how much you're shuffling the qubits around, I bet is reasonably comparable. Again, just because I have more ancilla doesn't mean I'm making syndromes faster. As for surface 10, you imagine that you have this guy moving around a lot and he could potentially be dephasing, but because he's getting reset a lot, maybe that's why you don't see a difference. Again, I don't have a great answer because we have a lot more analysis to do on that data.
So I'm concerned your performance of a 2-qubit gate after the movement, because I believe this phonon mode or interactions could be modified after the movement. So do you need to recalibrate your 2-qubit gate after each movement?
So I think that the question, after each movement, meaning I want to move my ions to the next position to do a gate, do I recalibrate? No. We do recalibrate a lot. There's a lot that goes into how we recalibrate, but to use an example, I don't work for IBM, but I have friends that do. I think IBM recalibrates like once a day. We recalibrate a lot more than once a day. We recalibrate quite a bit, but it's not as bad as in between individual gates.
Hi, firstly, thank for a really informative talk. So I have a question related to the decoding part, like why you are just working with minimum weight perfect matching. But, even there are very cool decoders which can be modified according to your error model. Like why just minimum weight perfect matching right now?
Because you got to start somewhere.
Okay. Okay.
So I guess we can take one last question from online. What is the average hidden cost of all-to-all connectivity? Or in other words, what is the cost of shuttling of ions which are physically far apart?
That's a really great question. So the easy answer is time, right? It takes time to shuttle these things far apart. And if you're as a qubit over here and there's a qubit over here, that's going to take longer than if they were a little bit closer. I think the other thing that's worth stating is that all-to-all connectivity is not long-term scalable. You're not going to have 1 billion qubits in a machine and have all-to-all connectivity. You might have different parts of the machine that are all-to-all or different variants of connectivity. And again, the cost comes into time and then complexity of the device itself.
Okay, thank you very much, Natalie. So we thank the speaker again. And so we have now second talk.